Hello, this is Eric from UNC Charlotte, and this is part 3 of our C++ crash course. Part 1 of our crash course was about basic types in C++, and part 2 was about objects in C++. Today I want to talk a little bit about function and functional programming in C++. As a reminder, this crash course is not meant to make you a C++ programming expert. The point of this crash course is to catch you up on what modern C++ can look like, so that you can later on go ahead and check the things that you need to learn. All right, let's get started. So let's start with basic functions in C++, and that mostly will come down from things that were feasible in C. Here you have a simple piece of code. We define two functions, f1, f2, that prints f1, f2. We define two other functions, f3 and f4, that take an integer as a parameter and are going to go ahead and print it. Nothing particularly surprising here. Let's look at what happens. In main, we call f1 and f2, so that does print f1 and f2. Something that you can do in C++ is use function pointers, and what those function pointers are, they are variables that can store the address of a function so that you can call that function later on. And the main goal of these function pointers is that you can actually assign them to different functions depending on what it is you need to do. The syntax come from C, and the syntax is kind of strange and confusing, but here it is. That's a line that declares a variable fptr, and fptr is a function pointer for a function that takes no parameter and that returns no parameter. It's a strange syntax for function pointer in C, but you'll see it from time to time, so it's probably useful to at least have seen it once so that you know you can recognize it and read the rule later on. And so what does this function pointer let you do? Well, you can set the function pointer to point to f1, and then whenever you're going to call fptr, it's actually going to call f1. You can set the function pointer to something else, maybe to f2, and that will enable you to, whenever you call it, it's gonna actually call f2. Why would you need function pointers? A good reason, for instance, would be whenever you call the quicksort function, quicksort would actually take a function pointer to know how to sort the things that are in the array. You can notice that these function pointers are also properly typed. If you try to get fptr to point to f3, you won't be able to do that, because fptr is a pointer to a function that takes no parameter and returns nothing, but f3 takes an integer, so you can't actually assign f3 to fptr. There are different syntax to do something like this. Here we define a different function pointer, fptr2, and you can see that in this case, that's a pointer to a function that takes an integer and returns nothing. And now we can actually set fptr2 to point to other things. If you're confused about how these function pointers work, personally, whenever I need one, what I do is that I use the auto syntax from C++, and let C++ figure out what the type of that thing is supposed to be. So function pointers are not used very often in C++. I mean, they're used sometimes, but not very often. And one of the main reasons why these function pointers are not used super often in C++ is because C++ has functor semantics. So what a functor is, it's an object that behaves like a function. And let's see exactly what we mean by that. So here we have an object. I call it my functor, and you can see it. So it's a regular C++ object, nothing strange about it. So it has some member variable, it has a constructor, but it also defines that parenthesis operator in a way that enables you to call this object as if it was a function, and that parenthesis operator takes no parameter and returns nothing, and it just prints something, and that's how you would use it. So you declare, you create a variable f of type myFunctor, and you can actually use it as if it was a function. Like you see, f it's a variable, it's not a function, but it's a variable of a type that defines parenthesis operator, and so it lets you use that variable as if it was a function. And that's why these types of variable are often called functors. Like they're not functions, but they behave like a function. And one of the good things about functors is that they do enable you to have a context to this function. So you can see, like here, we passed 314 as a parameter to the functor when we create it, so that whenever we call function f, we can actually retrieve the context, and you can see that it works correctly. And so these functors can define the function called operator with parameters. And here we have a separate one, it's myFunctor2, it works the same as myFunctor. The only difference is that it actually takes a parameter, here it's a double. And whenever you define f2, whenever you declare f2 of type myFunctor2, same thing, you have to pass some parameter to the constructor. Whenever you call f2, you can pass your double parameter to it, and it's going to go ahead and get printed. So people tend to use functors a lot more in C++ than everything else, than function pointers. And the reason why people use functors rather than function pointers is because functor enable you to have context that get passed to it. And functors are very heavily used in C++. All defined algorithms on collections, for instance, like for each, or find all the entries that have this particular predicate. They would take a functor as a parameter to define which objects we are going to return from the collection, or in which order we're going to sort things. My favorite addition to recent C++ about functions is the introduction of lambdas. C++ introduced lambdas, I believe, in 2011. And this really helps you do functional programming and programming that's a lot simpler to do. So here we see how that works. I defined some variable a, and here I have that strange syntax. And so let's unpack what that is. What is on the right is a lambda function, and that is the syntax for lambda function. If you want to know more about how the things work, go ahead and check the reference carefully about lambda functions, but here is the gist of it. Those brackets that open and close will indicate that we're going to be talking about a lambda function, and whatever goes inside the bracket is going to define which variables of function main, or the context of main, is going to be available for that function. And there are a lot of different options. Here I pick one in particular that's going to be good for this test. And essentially what that particular parameter means in the lambda function is that all the variables that are accessible to main will be accessible to this function as if they were passed by reference. And so that allows me in this function to simply call the ++ operator on A, and we can see later on whenever we are going to actually going to call a function f, we will see that the value of a is going to have changed. So here is how it goes. So function f is going to increase the value of a. Then we define a second lambda, we call it p. And what p is going to do is simply print the value of a. And the good thing is that now f and p are functions that are defined locally inside of the main function, and that allow you to easily do operation. And so if you have to do the things multiple times, then it's a lot easier to maintain. Now you can write whatever that small block of operation that you're going to do multiple times is, and you can just call it instead of having to copy paste it or things like this. That's one of the typical use of lambdas. Lambdas can take a lot of, can potentially take things as a parameter and can be used in a lot of other contexts. Here's another reason why you may want to use lambda. So I define a vector and I push some random values in it. Then I can define a function that is going to go ahead and print all the values of that vector. And you see that you would want to have that lambda because I'm going to need to have to do that twice, and so I wouldn't want to have to copy that code twice inside of my code. That's probably a lot easier to maintain, to have defined printv correctly, and to use it twice. So how does that printv lambda works? It actually works by calling the for each algorithm on the vector. That's how the syntax of for each works. If you don't understand how the syntax of for each works, check it on cppreference.com. And for each takes a lambda function. It takes a function. Very often people will write it nowadays using lambdas, but actually you could pass a function pointer or a properly defined functor somewhere. You can really do that. It really doesn't matter. And the way that the for each algorithm expect that function, it expects a function that will take a reference to whatever is stored in the vector and returns nothing. And so that's what this lambda is doing. That's a lambda that will take a reference to an integer. It's simply going to print this particular value and return. And so that what that for each is going to do is that it's going to go through all the elements of the vector from the beginning to the end of the vector, and it's going to call the lambda, the function that gets passed as a parameter to for each. And here what that function is going to do is simply print them. And that's the most common use of lambda that you will see in C++ code. They're actually passed as a parameter to an overreaching algorithm like for each. And here we have another use of lambda. If we want to go ahead and sort our vector, maybe we want to do a sort with some odd criteria. Maybe we want to sort the vector so that the odd elements are shown first and the even elements are shown next. And that's what that lambda function is going to do. That lambda function is going to be a comparator for two entries of the vector. It's a vector of int, so that lambda function is going to take two ints as a parameter. And here the logic is going to test whether A and B are even or odd, and based on that it will return so that the odd elements will go first and the even element will go then. And if the two A and B are both even or both odd, it will sort them in the natural order. And you can see that later on we could print V again, and we can see that originally the array was not sorted against that odd first criteria, but after we call sort, it is actually sorted correctly. So lambda functions are used very often in modern C++ codes in order to make code more modular without having to define a bunch of external functions that will pollute your namespace and your scoping space. Lambda functions are very commonly used. All right, so as soon as we start doing things like functional programming in C++, one of the things that people are going to want to do is to have functions that return multiple things at once. Unfortunately, in old C++, that was not easy to do. And what that code is showing you is the way people would be doing those things in old style C++, like in C++ 98. There was no easy way to return more than one thing out of a function. So what you would see very often is that people would write functions like this. They would write a function that would return one parameter and write something to a pointer pass as the second parameter. And people would be doing that to fake the let's return two values kind of thing. The idea is that you would return one on the stack and you write the other one to a pointer that get passed to you. And you will see that very often in C as well. Most function that needs to return something from the C library actually wants to return two things. They want to return the actual value that gets returned, but they also want to return some kind of an error code. And so very often what you will see is that this function will return an error code, and they will write the actual piece of data you care about to a pointer. Functions like comparisons, functions that will convert, for instance, a string to an integer. There's one called, I believe, str to L, and that's exactly what it will do. It will write to a pointer on an integer, and it will return an error code to tell you, oh, by the way, that did not go well, or something of that sort. It's a very cumbersome thing to do, and people didn't really like those notations, but people had to do that because there was no other choice. And so there is another reason why you may want to pass something by reference or by pointer in C++. And that other reason you may want to pass something by reference or by pointer is to avoid having to copy that object. Like, imagine that if you have to pass a parameter to a function that is a vector, maybe you want to pass a vector as a parameter. If you pass just a stud vector, then what the language is going to do is that it's going to copy the entire vector. And now if your vector is a vector of 1,000,000 entries, then copying 1,000,000 entries is going to be expensive. So what you would want to do is to pass a pointer or a reference to that vector so that you do not have to pay for that copy. But now that you pass something as a reference or a pointer, you don't know whether that downstream function is going to change the content of the vector. So what you would see very often in C++ is the convention that if you want to pass something at the parameter but you don't want to pay the copy, you would pass it as a reference on a constant object. Whereas if you expect the function to actually change the values that get passed, they would get passed as a pointer. And so you would see that very often in C++. You would see very often that convention where if objects are small, they are passed by copy. If objects are intended to be modified, they are passed by pointers. And if you're passing an object but you don't want to pay the cost of a copy, you'd pass a reference to a constant object. And you would see that very often in C++. So that's the state of things, of how things were in C++ 98. You would see these kinds of conventions very often, and you would see very often functions who want to return multiple parameters to return one on the stack and write to a pointer that was passed as a parameter. It turned out that we no longer really need to do that in modern C++. We no longer really need to do that in modern C++ because we can more easily use tuples as a type that gets returned for a function. And here is the basic of how things work. So you may want to have a function f, you may want to return two things, and so rather than return an int and write to a pointer, you'd return a pair, in practice, a pair of those two things. And here's how you would call those things. Maybe you just have two variables, a and b, in your program, and you want a to be the first that gets returned by f and b to be the second one. There is a feature of modern C++ that allow you to create some kind of an object that can be allocated a tuple. And so whenever f returns, what it's going to do is that the first parameter that gets returned is going to get returned to a, and the second parameter of f that gets returned is going to get returned to b, thanks to that tie here. And you can see that it works whenever we print it. That did print 2 and 3. people didn't really like that notation because it's kind of annoying to have to specify that stud tuple every time. But in practice, what you can do is set the return type of a function to auto as long as there is no ambiguity in the type. C++ will let you do that so that you can return your stud make tuple, but you don't have to specify exactly what the type of those tuples are. The type are going to be taken by the compiler automatically from the parameters that you pass to stud tuple, and you can see it works. It works exactly the same. Here we return 3 and 4, and so when we tie A and B to whatever gets returned by F2, we can see that they did get printed as 3 and 4. There may be cases where you don't actually care about one of the parameters, and so whenever F is going to return, it's still going to return 2 values, but maybe you don't care about one of them, in which case you can pass to tie one of those stud ignore that will just discard the value. The last feature of functional programming in C++ is to be able to bin parameters, and let's see a concrete use cases of how that would work. Here we have a function f that would take 2 parameters, a and b, and it's going to go ahead and print them. So you can directly call that function f with 2 parameters if you want. But maybe what you actually want is to have a function that only takes 1 parameter, because you know that for this particular context, the second parameter is always going to be this particular thing. So you just want to say, okay, I want a new function that only takes 1 parameter, and the second parameter it's always going to be this one thing. So you could do that in C++ with functors. You could create a functor object with the context of the second parameter. You could construct the object by passing that second parameter, define the function call operator to be able to do this. It turned out that thing is standard now. It's done for you by a function called studbind, and here is how studbind works. It takes multiple parameters. The first one is the name of the basic function that you actually want to call, and then you will get the list of all the parameters of that function. So here f has 2 parameters, so after f we want to have 2 parameters that will come. So the first one is something that we want to get passed to our object, so we'll set a placeholder for that. And the second one, we always want that parameter to be b. And so what foo is, it's equivalent to a function that takes only 1 parameter. And when you call that function foo, you will pass 1 parameter to it, which will go as the first parameter of f, and the second parameter of f will always be b, so that whenever you call foo of a, it's actually going to call f of a and b, and you can see that that's what is happening here. There are lots of reasons why you may want to bind things. Very often you want to bind things because you need to pass the output to some kind of a function parameter, maybe to a sorting function or to a for each structure or something like this. There is one that's fairly common, and that comes to us from numerical computing. Maybe you have a function g. Here g it's a cosine. And one thing that you may want to be interested in is to do numerical differentiation. And so, if you remember your basic calculus, to differentiate a function, what you do is, numerically at least, that you have some kind of a step parameter, and the differentiated value of that function at value x is going to be the function call of x plus step minus function of x, everything divided by step, and mathematically to get the differentiated number at x, you would compute the limit whenever step goes to 0. Here we are not going to be able to do that because we're going to do it numerically, and so whenever you want to differentiate, for instance, function g at 0, you'd pass a step that's very small. Here I chose 10 to the minus 4. And you can see that we get something that is close to the appropriate differentiate of G at 0. And the good thing with bind is that it allows you to directly bind the different parameter of that differentiate function so that we can get a function dg, which is numerically equivalent to the derivative of g. And now it's a proper function that we could use to do our calculation. So we can do numerical differentiation simply by defining the differential operator and by computing proper bindings, by using the language to proper bindings, we get something that behaves like a function. In practice, it's some kind of a functor on the back end, but it behaves like a function. All right, that's all I have for you today about functions in C++. And really what I wanted you to see about functions in C++ is that modern C++ actually enable you to write code that are very functional in nature because it supports Lambda function, it supports parameter binding, and it actually supports tying multiple return parameters to variables so that you can have function that returns many parameters and not just one like it was in C. That's all I have for you today. What we will talk about next time is what are the differences that you would see between C++ code that were written to interface with C and modern C++ codes. Goodbye.